Moving right along, let's look at the currents again. We have already seen these in the last chapter, where we said the Indian Ocean is unique because of its monsoonal reversals during the summer and winter months, whereas the Atlantic and Pacific Oceans have some similarities with the trade winds forcing an upwelling in the east and a pileup of warmer water in the west, which is much more dramatic in the Pacific Ocean. And the cute thing was that in both oceans we had currents going into the winds, which you probably cannot see clearly here, but we call them the North Equatorial counter current. We said the water gets piled up against the boundaries, and then there is a downslope gravity driven current that is held to be coherent because the northern hemisphere turns them into the equator, and equator is a dynamic boundary because the Coriolis changes sign across the equator, and you cannot easily cross the equator unless you can change the sign of rotation of the water with friction or something. Okay. With that, let's look at the wind stress over the ocean. In the surface, near the surface, you have the southwesterly winds, which cross the equator in both the Pacific and Atlantic Oceans and converge into the ITCZ, which you can see is clearly to the north of the equator, where the winds become weak. If winds are converging from both sides, they have to go to zero where they meet up, right? So that's what happens here. Here is the core of the northeasterly trades, the southeasterly trades, and as you go to the west near New Guinea and Philippines, you begin to get some monsoonal impact, so the winds become very weak. So the trade winds do not extend all the way to the West Pacific, which has consequences as we will see later on. The Atlantic is much smaller in zonal extent, so the winds ram right along into South America. And there we have our mid-latitude westerlies, as we kept saying, but they are actually southwesterlies, as you can see here, and you have some semblance of not very well organized polar winds. That corresponds to the fact that we had very weak meridional cells. And here is the Indian Ocean with just strong southeasterly trades to the south of about 5 to 10 south, whereas in the north the annual mean winds look very weak because you're averaging winds that are completely opposite in direction during the summer and winter. So when you average them, you get very weak looking winds. The other thing that becomes very important, as we will see soon, is the so-called wind stress curl. Okay, so when the winds are having a cyclonic or anticyclonic sense of curl, the rotation they can put into the ocean, that determines whether the ocean will be dragged by the winds into a anticyclonic circulation or a cyclonic circulation. So you can curl your fingers here around the trade winds, which are northeasterly and westerlies. So if you do that in the northern hemisphere, your thumb will point into the ocean, right? You can think of into the screen here. Z direction is up, so the curl is pointing into the ocean when you use your right hand rule. You should look up how to do the curls. We'll look at the mathematical formulation soon. What does this mean? We already know that the subtropical gyre is going clockwise, so it's an anticyclonic circulation, but winds are putting in a negative vorticity. The tendency of the ocean to rotate is clockwise, so it is in the negative z direction. Okay, that will become important as well. So basically that means that the waters are converging and being pushed down. You can also think of it in terms of the Coriolis. So winds are pushing the water westward here, so Coriolis will push it northward, whereas winds are pushing the ocean eastward here, Coriolis will push it southward. But remember that the F increases with latitude. So these eastward moving currents will move more to the south than these eastward moving currents that will turn to the north. So you have a net southward flow, as we will see. That also becomes very critical. This is just a animation of the winds, as the animation we will see next shows. The subtropical gyres become or the subtropical highs become larger and smaller with season as the ITCZ moves back and forth, north and south. Same thing happens with the subtropical gyres as well, whereas cold continent like Greenland tends to produce its own circulation because it has so much thermal inertia, right? So you can see the subtropical gyre and a less obvious subpolar gyre here. Similarly on in the southern hemisphere, you can also clearly see the channel configuration of the Southern Ocean, where wind can keep churning the ocean and the wind-driven currents can go all the way to the bottom. So the anticyclonic circulation and the pushing down of the lighter surface waters and the doming of the thermocline creates a high sea surface height in the subtropical gyres, and by the same token low sea surface heights in the subpolar gyre. Remember that when the thermocline domes down, troughs or goes down, sea level has to go up. Why? As we said, to keep the pressure gradient to near zero and to create basically no motion in the deep ocean, we need the two to compensate each other. So obviously you will have high sea surface height in the subtropical gyres and low sea surface height in the subpolar gyres. Okay, that is surface elevation and wind. So this is what relates the winds to the surface height. So winds are by friction producing circulation, which is converging the water and creating sea surface height, and then flow can go down the sea surface height as a gravity flow, which is our geostrophic flow. So I'll run through this again. Looking at the Hadley cell, we saw that it moves back and forth with the sun along, as well as moving the polar front, and here it shows a sense of the tropopause that drops off as you go from deep tropical convection regions to the subtropics. The red arrows are the converging moist air feeding the rising motion, and the upper air, cold air, moving towards the poles. We will add the ITCZ and run through the seasonal cycle just to remind ourselves. We have seen this before. We saw that the monsoon circulation creates the ITCZ to go way north over the Indian subcontinent. Here are the subtropical highs, which obviously will pump down and pump up depending on the Hadley cell. So the winter hemisphere tends to have the stronger part of the Hadley cell, even though the rising motion is over the Hadley cell, which is in the northern hemisphere in the summer. Doesn't always cross the equator everywhere. We have briefly mentioned it. We won't go into the details of why it's asymmetric, but one of the hypotheses is that because there is more land in the northern hemisphere, and land has lower heat capacity compared to the ocean, which is much more surface area in the southern hemisphere. But we'll see that ocean also moves energy to the north, and it turns out that the compensating southward energy transport in the atmosphere is done by the ITCZ, which can explain its northward position. That's just precipitation. Obviously there is monsoonal circulation and monsoon rainfall here. Greenish colors are high rainfall over the Amazon, East Coast, and parts of Tibetan Plateau, parts of Europe, Central America, Northern Australia, and Indonesian seas, and so on. Okay, that's kind of the summary of the winds and some of the circulations that it generates that will be related to the rainfall patterns and so on and so forth.